In part 2 of the Unit 5 notes, we will be covering organizing the elements. In 1649, Hennig Brand, a German alchemist, was attempting to extract gold from the human body. He boiled urine in hopes of isolating gold, but instead he created elemental phosphorus, which burned brightly and violently. While this was the first scientific discovery of an element, at the time he did not understand what he had done since the modern definition of an element was not yet developed. As alchemy eventually evolved into chemistry and the level of technology increased, the rate of discovery improved. By 1869, 63 elements had been discovered, and scientists began to look for patterns in the properties to organize the elements. In 1789, Antoine Lavoisier, also known for the law of conservation of mass, compiled a list of all the known elements and organized them into categories, including gases, nonmetals, metals, and earths. He was the first scientist to attempt to find patterns within the elements. In 1817, Johann Dobereiner noted that strontium had similar chemical properties to calcium and barium, and that its atomic mass was midway between the two. He later discovered two other triads, one consisting of chlorine, bromine, and iodine, and another consisting of lithium, sodium, and potassium. In 1829, he proposed the law of triads, which states that if you average the mass of two elements, and the mass of a third element matches the average, then those three elements should have similar chemical and physical properties. While Dobereiner's system would pave the way for future ideas, a limitation of the triad system was that not all of the known elements could be classified in this way. For our first checkpoint question, we are going to use the masses for lithium, beryllium, and boron to determine if they would have been considered a triad under the law of triads. Based on their position on the modern periodic table, we are also going to be evaluating whether their properties are actually similar. So in order to do this, we want to look at the lower average and the higher average. And we're going to determine if the average of those two masses is going to be equal to the mass in the middle. So if I take 7 plus 11, that's going to give me a total of 18 AMUs. I'm going to end up with 9, which is equal to the mass of the beryllium, which would be in the middle. Now, based on that, we could say that these three elements would be a triad. However, if we look at the modern periodic table, we have lithium, beryllium, and boron, which are all within the second row on the periodic table, or the second period. Elements that are in the same period do not necessarily have the same properties. Elements that are similar to each other would be in the same family or group going up and down. So these elements do not have the same properties. So this right here shows that the law of triads does not always actually work, because in this instance, we were able to create a triad, but based on our modern knowledge of the periodic table, we know that they actually would not have similar properties. In 1864, English chemist John Newlands ordered the elements in increasing order of atomic mass, and noticed that every eighth element exhibited similar properties. He named this periodic relationship the law of octaves, based on the musical octave in which notes repeat every eighth tone. While the law fit well for smaller elements, it did not hold for elements larger than calcium. There was also an entire family of elements which had not yet been discovered at this time, which means his pattern would have actually occurred after every ninth element. If you look at the diagram shown here, you can see that it is color-coded. So lithium would have properties similar to sodium. Beryllium would be similar to magnesium, and so on. For our next checkpoint question, we are looking at the pattern, which shows elements in order based on atomic mass. We are trying to figure out the family which is missing from this pattern. Now these are all in order by mass, so we can use the modern periodic table in order to help us understand which elements would be missing. So between element 1, which is hydrogen, and element 3, which is lithium, we would have element 2, which is helium. So helium would be inserted right here. Between fluorine and sodium, we should have neon. And then after chlorine, we should have argon. So the family of elements, helium, neon, and argon, which are missing from this ordering, would be the noble gases. The noble gases were not discovered until later. That concludes part 2 of the Unit 5 notes. When we come back in part 3, we will be looking into creating the periodic table and periodic law.